Good afternoon everyone. Today we are going to start a lecture on fuzzy relations and rule base. The outline of this lecture will be fuzzy relations with some example and fuzzy implications relation. Then we will get into the fuzzy rule base, which forms the fundamentals of fuzzy logic, and then we will have finally multiple rules of fuzzy system, precisely a continuous fuzzy system. Now coming to the fuzzy relations, let us talk about that. If x and y are two universal sets or universal sets, the fuzzy relation R of x comma y is given by R of x comma y equal to mu R of x comma y upon x comma y, such that x comma y belongs to x cross y, that is the set or the set involving the universal sets x and y. Thus the fuzzy relation is given by R of x comma y equal to mu R of x comma y upon x comma y, such that x comma y members belong to the universal sets represented by x cross y. Now coming to the formal definition of fuzzy relations. A fuzzy relation is a fuzzy set defined in the Cartesian product of crisp sets say x1, x2, x3 up to xn. Okay, this is a formal definition of a fuzzy relation. It is a fuzzy set defined in the Cartesian product of crisp sets x1, x2 up to xn. Now the fuzzy relation R of x1 comma x2 comma up to xn is given by a formal expression mu R of x1 comma x2 comma x3 up to xn upon x1 comma x2 comma x3 up to xn, such that x1 comma x2 up to xn belongs to the product of x1, x2 up to xn. This is the formal expression for a fuzzy relation, where mu R is defined for the multiple universal sets x1 into x2 into x3 up to xn will take a value in the interval between 0 and 1 is the membership function value mu R. Now let us see the relation inference. Say fuzzy relation represented by R1, R2, R3, where R1 is relating the Cartesian space of two universal sets x and y, where R2 is the relation, fuzzy relation relating Cartesian space y and z, and R3 is for Cartesian space relating x and z. So R1 is associated with the Cartesian space formed by x and y universal sets, likewise for R2 and R3. Now if R1 and R2 are given, then R3 can be inferred using the following relation, or you can say precisely following operation. One is fuzzy max min composition operation, another one is fuzzy max product composition operation. Max product composition operation. Either of these two operations R3 can be inferred given the relation R1 and R2. Okay, now let us see what is fuzzy max min composition. The first one let us take fuzzy max min composition operation. We can see this with an example. Let us consider two fuzzy relations. Let us consider two fuzzy relations R1 and R2 defined on the Cartesian space, you can say Cartesian spaces x cross y and y cross z respectively. That means R1 is defined on the Cartesian space x cross y and R2 is defined on the Cartesian space y cross z. Okay, so now the max min, the fuzzy max min composition of R1 and R2 is a fuzzy set defined on the Cartesian space, that is the max min composition of R1 and R2 is a fuzzy set defined on the Cartesian space x cross z as R3 equal to R1 composition R2, which is given by mu R3 of x comma z upon x comma z. Okay, so here mu R3 of x comma z is given by a main expression maximum over y of minimum of mu R1 of x comma y comma mu R2 of y comma z such that we can say x belongs to capital X, y belongs to capital Y and z belongs to capital Z. Okay, so this is the formal definition and expression for fuzzy max min composition operation. Okay, so that is given by this expression R3 is obtained as a composition of R1 and R2, which is given by this expression where the numerator mu R3 of x comma z is given by max of minimum of this membership functions corresponding to the two spaces. Now let us see an example to understand this problem. Example to understand this max min fuzzy composition operation. Say we have R1 equal to between the x and y sets of the Cartesian space. So, it is R1 is defined on the Cartesian space having x and y universal sets. So, they are having the relation matrix given by 0 0.1, 0 0.2, 0 0.4, 0 0.5 and 0 0.7, 0 0.8 let us say. And let us say R2 is obtained by or is defined on the Cartesian space of y and z sets. So, y is in the row and z for the column of this matrix. So, they have the elements 0.9, 0.8, 0.7, 0.6. So, then we have R3 obtained with the dimension R3 is meant for x and z. So, 3 cross 2, this is for x and column for z, x cross z. So, let us say that R3 of 1 comma 1, what is that, is obtained by max of minimum of 0.1 comma 0.9, 0.9, this row you take and then this column. So, 0.1 and 0.9 minimum of that, similarly minimum of 0.2 and 0.7, okay, this and 0.2 and 0.7, take the maximum of that. So, maximum of 0.1 comma 0.2, what is that, it is 0.2, similarly we can do for other element or 1 comma 2. So, in that way if we do, we will be ending up this matrix R2 or 3 to be 0.2, 0.2, 0.5 and 0.5 and 0.7 and 0.7 by fuzzy max min composition operation. Now, let us talk about the fuzzy max product composition operation. Okay, let us see that now. Fuzzy max product composition operation. With the same example we can take, but before that let us see the expression, or it is defined the fuzzy max product composition of R1 and R2 is a fuzzy set defined by R3 equal to R1 product of R2, which is nothing but mu R3 of x comma z upon x comma z, that is all, where mu R3 of x comma z is given by maximum over y of mu R1 of x comma y multiplied by mu R2 of y comma z, that is all. Okay. This is for fuzzy max product composition operation. Okay. So, now we will see the example given by the previous R1 and R2s. Okay. So, now again we take an example where R1 is again given by the matrix for x and y, that 0.1, 0.2, 0.4, 0.5, 0.7, 0.8, and R2 is given by y cross z. So, it is given by 0.9, 0.8, 0.7, 0.6. So, by fuzzy max product composition operation, we can get R3 coming out to be 3 cross 2 matrix, 3 rows and 2 columns. Okay. So, now what is R3 of 1 comma 1? It is given by max over y of 0.1 into 0.9 comma 0.2 into 0.7. So, the maximum of 0.09 comma 0.14, which is 0.14. So, this guy is 0.14. The element R of or 3 of 1 comma 1 is 0.14. Likewise, we can get the other elements as 0.12, 0.36, 0.32, 0.63, 0.56 for R3 using fuzzy max product composition. Okay. So, now you can cross check these answers. Okay. Now, let us see which involves some deeper understanding that we have two relational matrices. We get the third relation matrix obtained from the practical situations. Okay. So, let us consider this example 1. Okay. So, let us see this example. Let X be an universal set of well known objects given by X equal to car, boat, church, bike, tree and a plateau. Okay, there are 6 elements of this universal set: car, boat, church, bike, tree and plateau. Again, let Y be universe of simple geometric shapes, that is given by Y equal to square, octagon, triangle, circle and ellipse. Okay, there are 2 sets defined now, which are called universal sets. Okay, so now let us define a simple fuzzy set, okay, of objects such as car, square and edges. Each one is a fuzzy set. A simple set car and another simple set Z square and the third simple set is edges. Okay, so that is represented as, say, A is a fuzzy set which is meant for car, which is given by membership function value upon element 1.0 upon car, because the membership function value of car for the fuzzy set car is 1 and 0.4 upon boat. Similarly, 0.1 upon church and 0.6 upon bike and 0.1 upon tree and 0 upon plateau. Okay, likewise, we have the fuzzy set called square, which has the value 1 for square, 0.5 for octagon and 0.4 for triangle and 0 for circle and 0.1 for ellipse. Okay, so these are the 2 sets defined now. Now, let us see the third set as C equal to edge, which is given by 0.6 upon square and 0.9 upon octagon and 0.4 upon triangle and 0 upon circle and 0.2 upon ellipse. Okay. So, these are the three sets we have, fuzzy sets we have defined now. Now, let us have the question Q1, find a relation R that is between car and square. Likewise, question 2, find a relation, let us have this as S between square and edge, between the first and second fuzzy set, and between the second and third fuzzy set is relation matrix S. And then question 3 is using max min composition operation find a relation T between car and edge. So, now T has to be found between car and edge, that is the question now. Now, let us see that how it is getting done. Okay. So, now let us move on to the solution now. The solution is the matrix, the relation matrix R is the fuzzy set A and B. Okay. So, that is R is the relation matrix that is between the fuzzy sets A and B. So, now let us see how R can be obtained. R equal to, which is given by a matrix that is meant for fuzzy sets A and B relation. So, A has, what are the names A has, what are the elements? A has car, boat, church and bike, tree and plateau. So, we can write them in the column car, boat, church, bike, tree and plateau. Okay. So, this is the thing for set A and this is for set B, fuzzy set B. So, that is square, octagon, triangle and circle with ellipse in the end. Now, let us form this relation matrix R that is between sets A and B. Now, let us see that the fuzzy set A, what value it was having. Accordingly, we can see that which one is the minimum obtained here. Okay. For 1 and 1 here, which is the minimum. So, this is 1. Likewise, the minimum entries between the fuzzy set A for each of the fuzzy sets of set B, or the elements or the variables of the fuzzy set B is compared. Which one is the minimum? We can enter here. Okay. The car for the shapes. Okay. Car for square is getting 1 and octagon, triangle are getting, as per the minimum value we are getting the first row filled as 1, 0.5, 0.4, 0 and 0.1. And likewise, for boat, for all the shapes, 5 shapes, we are getting the value which is nothing but the minimum of these 2 values. It is getting as 0.4, 0.4 and 0.4 with 0 and 0.1. Likewise, for church member, we are getting 0.1, 0.1, 0.1, 0 and 0.1. Likewise, for bike, we are getting 0.6, 0.5, 0.4, 0 and 0.1 for the corresponding shapes. Finally, for tree, we are getting 0.1, 0.1, 0.1, 0 and 0.1. Likewise, for the plateau, it does not come under any shape. So, we can say 0, 0, 0, 0 and 0 is a minimum value as compared to that. Okay. So, likewise, we can go for computing the matrix S, that is between the relation between the fuzzy sets relation matrix between the fuzzy sets B and C. Okay. So, in the same manner, S matrix is going to be obtained as this one, and we have the columns meant by these shapes, that is square, octagon, triangle, circle and ellipse. Likewise, the edge which is for C subset or C fuzzy set is having the edge which is also having the shapes based square, octagon, triangle, circle and ellipse. Okay, now let us find the relationship between these two fuzzy sets and name it as matrix relation matrix S. So, when we compare that and put the minimum, we get 0.6, 0.9, 0.4, 0 and 0.2 as the first row, and 0.5, 0.5, 0.4, 0 and 0.2 for the second row, which means we are comparing and taking the minimum and putting here. So, likewise, the third row of this S matrix is coming to be 0.4, 0.4, 0.4, 0 and 0.2. Likewise, C is having circle, is having all the elements coming out to be 0, and finally, the ellipse value is getting 0.1, 0.1, 0.1, 0 and 0.1. So, now we finish with the examples to get the relation matrix R and S, but we need to get the relation matrix T, that is obtained by the fuzzy max min composition rule between the matrices R and C. Let us see that now. So, T is obtained by fuzzy composition between the relation matrix R and C, R and S. Okay. So, it is basically to get the relation between fuzzy sets A and C basically, and that one we need to use fuzzy max min composition. We can use, we need to use fuzzy max min composition to obtain this table called relation matrix between R and S. So, let us have this table form now, R and C. Okay. So, it is basically R and S. Okay. So, R forms the rows and C forms the columns. So, car, boat and church, then bike, tree, plateau, and S has square, octagon, triangle, circle and ellipse as the members. So, we represent here. Okay. Now, let us see T11, this one we need to find it now. Now, let us see T matrix of 1 comma 1 is obtained by max of minimum of 1 comma 0.6, minimum of 0.5 comma 0.5. I am comparing these values, where I am taking these values from the R and S matrices, taking the first row of R and comparing that with the first column of the S matrix. So, I am getting these entries, which is nothing but maximum of minimum of 1 comma 0.6 and 0.5 and minimum of 0.5 and 0.5, and then minimum of 0.4 and 0.4, then minimum of 0, 0 and minimum of 0.1 and 0.1. Okay. So, that leads to maximum of 0.6, 0.5, 0.4, 0 and 0.1, which is nothing. What is the maximum? 0.6. So, the first entry of this T matrix is going to be 0.6. Likewise, we can fill this table of T matrix, which is going to be 0.6, 0.9, 0.4, 0 and 0.2, and this first row is obtained by taking the first row of R matrix, compare with each column of the S matrix. Similarly, taking the second row of R matrix and comparing that with all the 5 columns of S matrix, we get the second row of T matrix 0.4, 0.4, 0.4, 0 and 0.2. Then third row is coming out to be 0.1, 0.1, 0.1, 0 and 0.1, and fourth row is 0.6, 0.6, 0.4, 0 and 0.2. Finally, the fifth row is 0.1, 0.1, 0.1, 0 and 0.1, and the last row for the plateau is 0, 0, 0, fully filled with 0 elements. Okay. So, like this we have completed the relation matrix to obtain through fuzzy max min operation composition. Okay, composition operation. Alright, now let us talk about something called fuzzy linguistic variables. That is very important to construct the fuzzy rules. Let us see that now. Okay. So, now let us talk about fuzzy linguistic variables. Fuzzy linguistic variables. We know that algebraic variables take numbers as values, whereas fuzzy linguistic variables, they take words or sentences as values. Okay. So, now let x be a linguistic variable with label height. X be a linguistic variable with label height, which means x is a linguistic variable which is mentioning or representing height as a label. The fuzzy set height, say denoted by capital H, can be written as H equal to very short, medium, tall, very tall. Okay. So, this is the fuzzy set called height represented by H with its fuzzy variables, precisely fuzzy linguistic variables, very short, medium height, tall and very tall. Here height is the base variable which is called the universe of discourse, and each term or each item in the fuzzy set, very short, medium, is a linguistic value of the fuzzy variable x. That means the fuzzy variable is x, it's a linguistic variable which has a value that is very short, short, medium, these things. Okay. So, with this let us have a discussion about further things on fuzzy rule base and fuzzy implications relations. Okay. So, now we will see fuzzy rule base. Having defined the fuzzy linguistic variables, we see fuzzy rule base now. So, fuzzy rule base, it is also called if then rule base. Okay. So, fuzzy rule base is one way to represent knowledge through natural language. The generic form of a rule base is if premise then conclusion. If you have an introduction, then conclude it. Fuzzy information can be represented in the form of rule base, which converts a set of rules, which consists of rule base is having a set of rules in the conventional premise conclusion form. Okay. That means introduction conclusion form. Rule base is nothing but a set of rules, and each rule is having if then rule base, which is in the form of conventional premise and conclusion form. Let us talk about a rule. Say rule 1, it is given by if x is A, then y is B, where A and B are representing fuzzy propositions or fuzzy sets. Okay, or fuzzy sets. Okay, propositions. Okay, fuzzy propositions or fuzzy sets. Precisely, they are nothing but the membership function values pertaining to that rule. We are going to see that them in the upcoming time. Okay. So, this is rule 1. Okay. So, we can say that we now introduce a new introduction or premise, say A1, and we consider the following rule, say rule 2, if x is A1, then y is B1. Now, the question I have here is, we have two rules, and the first rule is if x is A, then y is B. Likewise, rule 2 is if x is A1, then y is B1. So, from the information of rule 1, information can we derive the consequent, say B1 of rule 2? That is a question. The answer is yes, by composition operation. Okay, that is obtained by composition operation. How it is? Say we need B1, which is nothing but A1 composition the relation matrix R. Okay, so I can write A1 here, A1 composition R. Okay, so it is not the superscript, it is the subscript. Okay, so we have coming out this, that from the rules we can get the consequent of the next two rules by composition, fuzzy composition operations using the relation matrices. Now let us talk about fuzzy implication relations. Let us talk about fuzzy implication relations. So, a fuzzy implication relation for a given rule, if x is ai, then y is bi, is formally represented by Ri of x comma y equal to mu Ri of x comma y upon x comma y. Okay. Mu Ri, you know that it is a membership function value. So, the fuzzy implication relation is, let us consider a rule which is x, if x is ai, then y is bi, is formally represented by Ri of x comma y equal to this. Okay, so here mu Ri of x comma y is the membership function constituted using implication rules, that is, if P then Q. Okay, so one of the implication rules, okay, so one of the implication rule is, one of the implication, there are several rules, I am considering here in this lecture only one rule, implication rule, which is Mamdani implication rule. Okay, so that states that when fuzzy if then rules are locally true, then using Mamdani implication rule we can say that P tends to Q implies P and Q is true, that is taking the AND operations between the membership functions of that rule. Okay. So, by having the membership function values and taking the AND operation of that rule, we can get the fuzzy Mamdani implication rule. Okay, we can understand the rule implication, fuzzy implication relations by Mamdani implication rule in such a way that when a fuzzy if then rules are locally true, then it implies that P tends to Q, which means that P and Q are AND operated. Okay, that means we are going to choose a minimum value of the membership function corresponding to P and the membership function corresponding to Q. Okay, now let us talk about fuzzy compositional rules. Okay, let us talk about fuzzy compositional rules. So, there are different rules, okay, so that to get a matrix B by the composition operation between A and matrix A and R. Okay. So, let us say max min fuzzy compositional rule, which is given by max min fuzzy composition rule is given by mu B of y for this relation B equal to A composition R. For that, the fuzzy max min composition rule is given by mu B of y equal to maximum over x belonging to capital X of minimum of mu A of x. Okay. So, mu A of x comma mu R of x comma y. Okay. This is it. Similarly, max product, instead of in max product the minimum inside the bracket will be replaced by the product. So, the max min fuzzy compositional rule is given by mu B of y equal to maximum over x belonging to capital X mu A of x multiplied by mu B of mu R of x comma y. Okay, likewise, we can go for max fuzzy compositional operation and minimum fuzzy compositional operations also. Let us take an example here that if capital if x is A, then y is B, where A is given by a fuzzy set is given by 0.2 upon 1, 0.5 upon 2, 0.7 upon 3, and let us say B is given by 0.6 upon 5, 0.8 upon 7, 0.4 upon 9. Now, through fuzzy implication, how can we infer B1 for the following rule? So, now we have the following rule is if x is A1, then y is B1. Okay, so, now the question is how can we get B1 from the rules we have. Okay, definitely we have to do the composition operation. Here A1 for this rule equal to 0.5 upon 1, 0.9 upon 2, 0.3 upon 3. Okay. So, we need to have the relation matrix first of all. Okay. So, that relation matrix it is between A and B. So, the first rule is having the statement if x is A, then y is B, where A and B are given, and we have the second rule if x is A1, then y is B1. Now, we need to find or infer B1 from these rules through fuzzy composition operation using max min. Let us say we have A1 2. Now, the solution is using the Mamdani, the solution is using Mamdani implication relation. We have the R matrix coming out to be X, this is for Y. The X corresponds to the elements 1, 2, 3 and the Y corresponds to elements 5, 7 and 9 as per the rule 1. So, we take the minimum of these two elements corresponding to these two fuzzy sets. So, 0.2, 0.2, 0.2 and 0.5, 0.5, 0.4 and 0.6, 0.7, 0.4. So, here you must know that the elements mu or I of x comma y is obtained by minimum of mu a I of x comma mu b I of y. That is how we are getting these elements 1, 2, 3, 4, 5, 6, 7, 8, 9 elements we are getting. Now, let us see using the max min compositional relation or operation, we can have B1 equal to A1 composition relation matrix R. So, that is nothing but maximum of minimum of mu A1 of x comma mu R of x comma y. So, B1 is going to have B1 of 1, the element, first element we are going to find maximum of minimum of 0.5 comma 0.2 comma minimum of 0.5 comma 0.5. You can remove this bracket. So, third one minimum of 0.5 comma 0.6, which is nothing but maximum of 0.2, 0.5 and 0.5. It is 0.5, that is B of 1 is 0.5. Likewise, we can find B of 2, which is going to be by this expression, that is B1 of 1, B1 of 2 is nothing but maximum of minimum of 0.5 comma 0.2 and then minimum of 0.5 comma 0.5 and then minimum of 0.5 comma 0.7, which turns out to be maximum of 0.2, 0.5 and 0.5, that is finally 0.5. Likewise, we can do for B of B1 of 3, that is coming out to be 0.4. So, finally, we can say that B1 is obtained as 0.5 upon 5, 0.5 upon 7 and 0.4 upon 9, that is all. Okay, because B1 is a A1 related to R1, composition relation between A1 and R1, that is coming out to be 0.5 upon 5, 0.5 upon 7 and 0.4 upon 9. Okay. Now, let us see multiple rules, the final topic we have come here, we will see in the new slide. Multiple rules with continuous fuzzy sets. Okay. Now, let us take two rules. Take the following rules. Rule 1, which is given by rule 1, such that if x1 is A11 and x2 is A21, then y is B1. Likewise, rule 2, if x1 is A12 and x2 is A22, then y is B2. You must be noting that in both the rules I kept a uniformity, that the superscript is for corresponding rule. So, you also maintain the same thing to avoid confusions in the numerical problems. So, here A11 and A21 are the values of the fuzzy input variables x1 and x2 of rule 1, and B1, B2 are the fuzzy output values of rules 1 and 2 respectively. Okay. So, this is a continuous fuzzy set. So, this is a, this system is a continuous fuzzy system with two non-interactive inputs, say x1 and x2, and single output, which is y. Okay. So, now this is the definition about this system with these two rules. Now, finally, let us come to an important part here, which is drawing the membership functions. Let us see the pictorial representation of rules 1 and 2. There is a very important concept here. This is membership function for rule 1, here we are doing. So, say this is crisp value, crisp input x 1, okay. So, which has the membership function value that is a 1 1. Then for the second input x 2, we have a again triangular membership. For this corresponding crisp value, we have here, that is a 2 1, sorry, a 2 1. This is the crisp input x 2. For these corresponding crisp inputs, we get the membership function value as a 1 1 and a 2 1 for inputs x 1 and x 2 in rule 1 respectively. That leads to an output mu, which is a membership function. Okay. So, here comes the a 1 1 and a 2 1. The minimum of this comes here in your output, that is B 1. This portion. Okay. So, this is now first rule's output B 1. Likewise, for rule 2, we have membership function, let us say this is the crisp input, that leads to a 1 2 is the membership function value corresponding to that a x 1 input. Now, we have for input x 2, for that corresponding crisp input of x 2, we have the output that is coming out to be a 2 2. Okay. So, now this leads to the output membership function for y. So, the minimum of this goes here. So, the minimum cuts here. So, this portion gives you the B 2, that is the output 2 for rule 2. Now, the resulting output membership function is given by the maximum of this and this. You get the output of rule 1, it is a minimum of these two function values of corresponding inputs x 1 and x 2. Likewise, for rule 2, membership function value for rule 2 for x 1 is a 1 2 and for x 2 it is a 2 2, minimum of that form the B 2, that is the output for rule 2. Now, the resulting output membership function is given by the maximum of these outputs for each rule. So, the maximum case here is mu is y axis, x axis is y. So, add this. So, from here you can see the value obtained from this output membership function y star. So, in general the output value is obtained, that is the crisp output is obtained by a method called center of gravity approach. By that you can obtain y star, which is coming out to be integral y mu of y dy upon integral mu of y dy. So, this is called center of gravity approach. By that we can get the final crisp output of this problem. Okay. So, now coming to the conclusion, we have seen today fuzzy relations, fuzzy implications relation, fuzzy rule base, and finally multiple rules for a fuzzy continuous system. In the next class we will be seeing on fuzzy logic control of robotic systems. Thank you very much.